Hello, so in this video we'll talk about how to compare the means of two populations or two groups using a t-test. So the method that we use or the strategy that we take depends on whether or not we want to use what are called paired samples or independent samples. The decision comes down to how our data may be related. So let's talk about the difference between these two. For paired data, we've got two observations or two sets of observations that we'll consider paired if each observation in one set has a one-to-one correspondence or match with a single observation in the other data set. A great example of paired data in the health sciences is twin studies, studying one twin versus the other. Those are two natural pairs. Another good example is when the same subjects are actually used, but before and after measurements are taken. So measurements before receiving some drug versus after receiving should be considered paired data as well. Now compare that to independent samples. We say that two samples or two sets of data are considered independent if there's no relationship between observations in group two or in each group. So if we take patients from one hospital and compare them to patients at another hospital, there should be no relationship or linkage. So those are independent samples. Whether or not we have paired data versus independent data tells us how to analyze the data. So that's why it's important to take this step and think about where the data came from. So let's talk about how to handle paired data first. So I'll let x1i represent the ith observation in group 1 and xi2 represent the ith observation in group 2. For each observation, I'm going to calculate a new variable called the difference. We'll just take the measurement in group 1 or column 1, subtract the measurement in group 2 or column 2, and then this new difference becomes the variable that I care about. With this new difference variable, I can proceed exactly like we did in the last section. I can do confidence intervals, I can do hypothesis tests, now with a difference variable. So for example, we can calculate a confidence interval by treating the difference variable as our new variable of interest. So take d bar, we'll calculate the standard error of the differences, and then apply a t interval. So let's take a look at an example of a study using paired data. Non-digestible oligosaccharides are used to stimulate or encourage calcium absorption in rats. We wanted to know whether or not this had a similar response in healthy male adolescents. So subjects were recruited to take place in a double-blind randomized experiment in which they took a pill for 9 days and had their calcium absorption measured on the last day. The experiment was repeated 3 weeks later, so the same subjects actually received both pills. The order changed. Some patients got the oligofructose pill or the treatment pill in the first round, control or placebo in the second. For other subjects, the order was switched. So let's take a look at how this data is structured. We've got 3 columns in this. This is the oligofructose data set. We have the subject, we have calcium absorption in the control condition, and calcium absorption in the oligofructose condition. For each subject, I need to calculate a difference, and I can do this either way. I've chosen to do it control minus oligofructose. So for subject 1, what's my difference? Well, it'll be 78.4 minus 62.0, so it will be 16.4. Subject 2 has a negative difference, indicating their oligofructose measurement was higher than the control, and so on. So we'll calculate this difference for all subjects in the study. Looking at the individual groups, so we haven't done the difference yet, comparing each of them, the average for this control condition looks like it's lower than the average for the oligofructose condition. So maybe there's some evidence that calcium absorption is increased or encouraged. To calculate a new difference variable, I'm going to use a mutate function. Mutate calculates or creates new variables. My difference is just control minus oligofructose. Again, I'll use the skim function to take a look at the summary statistics. Notice that the mean of the difference variable should be what you get when you take the mean of control minus the mean of oligofructose. So the difference of the means should be the same as the mean of the difference. So let's calculate and interpret a 95% confidence interval for this difference. Well, using the skim function, I've got my mean, I've got my standard deviation. I know my sample size is 11. Because I want to use a t method, I do need that t value. So we'll use QT, DF, degrees of freedom, are 10, 11 minus 1. P, this is our confidence interval shifted slightly, so for a 95% confidence interval, we'll use 0.975 here. So this gives me a T multiplier of 2.23. So we'll plug everything into our equation and come up with the following confidence interval. We're 95% confident that the population mean difference is between -23 and 1.36. Now look at how we defined this difference. Our difference is control minus oligofructose. Most of the values in this confidence interval are negative, which would indicate that oligofructose had a higher calcium absorption. However, because the confidence interval does contain 0, it's possible that the mean difference is exactly 0, which would mean that the two groups were effectively the same. So we can't really make a compelling certain statement with this confidence interval. We can, if we would want to avoid calculating the confidence interval by hand, we can certainly do this in R using the t.test function. So here my variable is difference, confidence level 95%, data is the oligofructose data set. We get the same confidence interval that we would have calculated by hand. So let's take a look at how we would frame a test for paired data. Just like the confidence interval, we'll work with this new variable, the difference variable. So the paired t-test is the name of this procedure, and it tests the null hypothesis that the population mean difference is equal to a specific value. Most of the time, this should be 0, and here's why. If this difference is 0, then that means that the two groups are essentially the same. If the average difference is 0, then there's really not much distinction between group 1 or group 2, or treatment or control. So most of the time, but again, not always, we'll use 0 as the number in these hypotheses. So our null and alternative hypothesis look very similar to before. Now we're just using the difference variable. We have it equal to whatever we assume, usually 0, less than, greater, not equal are the choices for the alternative. We'll calculate our test statistic. Formula looks exactly the same. Now we're just calculating these numbers based on the difference. We'll use t-test for our function, exactly the same. We'll make a conclusion in the same way. So let's jump right into our example. Is there enough evidence to show that the treatment encourages or stimulates calcium absorption? So our difference, remember we calculated this as control minus oligofructose. So if the difference is negative, the control group has less absorption, the treatment group has more absorption. So that's why we'll use a less than in the alternative hypothesis. We'll calculate our t-test using this less statement here. Our mean is 0. Here's our result. Our p-value is about 0.04. There's some evidence that the treatment group has higher calcium absorption. There is a hesitation, and I apologize because this got left off of the slide. But where do you think this hesitation's coming from? Think back to our sample size. The degrees of freedom are 10, so that means we had a sample of only 11 individuals. So yes, this is a somewhat small p-value, but we don't really have a lot of information. So as a statistician, I'm not really convinced by this data. One thing I do want to point out, we can actually skip calculating the difference column if we would like. So another way that you might see this test done is by feeding in 2 columns instead of 1. Unfortunately, to do this, we need to use $sign notation, and here's how you read this. So from the oligofructose data set, we extract, so this $sign means pull out the control variable. From the oligofructose data set, we extract the oligofructose variable. And then we need to tell R that these are paired observations. This gives you the same output, but I don't really recommend it. And I don't really recommend it because it's a little bit more complex. You have to extract variables from your data set each time you do this. It's certainly a lot more difficult to read as well, so I prefer to calculate the difference first. Now let's talk about what happens if you're in the other situation. What happens if you've got independent samples? So we'll let x1i again be the ith observation in group 1, x2i the ith observation in group 2. This time we're not going to calculate a difference. These two groups do not correspond. In fact, they probably don't have the same number of observations. So we'll have a sample mean for each group, x bar 1, x bar 2. We'll also have a sample size for each group, n1, n2. It turns out that this difference in the sample means follows a t-distribution, so that's good. The standard error of this t-distribution is a little bit tricky, and it rests on whether or not we're willing to make an assumption. So, if we're willing to assume that both groups in the population have the same standard deviation, then we'll use this option. Then we'll estimate the variability of this distribution using what's called the pooled standard error formula. In R, we'll write var.equal true. Variance is another term for measuring the variability of a distribution. Variance is standard deviation squared. So those two numbers are intrinsically linked. However, if we're not willing to make this assumption, then we have to use a different standard error formula called the unpooled standard error formula. This goes by 2 other names, the Welch approximation or sometimes the Satterthwaite approximation. In R, we'll denote var.equal false to assume that the populations don't have the same variability. The formulas for each of these standard error representations, pooled versus unpooled, are in your notes, they are in your textbook. However, we'll leave the details to R to calculate. So the confidence interval for the difference of population means, again, looks really similar. We've got the difference in means, we've got the t times the standard error. Here's the question we have to ask ourselves. What standard error do we use? Here's the rule of thumb I like to take. So if the ratio of the bigger standard deviation to the smaller standard deviation, if that's greater than 2, then I recommend using the unpooled standard error or writing var.equal false. So if this ratio is greater than 2, then we cannot assume the variances are equal. However, in practice, the results are pretty darn similar. So let's take a look at an example with some independent samples. So according to the CDC, obesity rates have increased pretty dramatically over the last 3 decades. One potential cause or solution to this might be family-based food counseling sessions to help families eat healthier. So the study randomly assigned obese children between the ages of 9 and 12 and their families to either this food counseling intervention session or a control group. There's a data set called obesity that includes the weight changes in pounds after 15 weeks. So we've got the control group that did not receive any counseling and the intervention group which did. Now, remember, this is only a 15-week period, so we shouldn't expect to see large changes in weight. Looking at the control group on the left, it looks like only one member of the control group lost weight, had a negative weight change over that time. In fact, most of them had a slight increase in weight. Compare that to the intervention group. Most of the children in that intervention group lost a few pounds. The peak seems to be right at about 4 pounds, which is a safe weight loss over a 15-week period. There were some who gained weight during that time as well. Looking at each of the groups, we see these same patterns in the histogram play out. So the control group, on average, slightly gained weight, gained about 3.5 pounds over the 15-week period. The intervention group lost weight, lost about 2 pounds on average. Notice the sample sizes are pretty different for these two groups. There's 23 children and families in the control group, 52 in the intervention group. So what I'd like to do is see how these confidence intervals change or compare depending on what technique we use. So if we don't assume that the groups have the same standard deviations or the same variability, we end up seeing a confidence interval that goes from about 3.5 to about 8.1. The default in the t-test function is not to make this assumption. However, if we want to assume, or if we're comfortable assuming that the two groups do have the same standard deviation, then we'll add this var.equal true, and we'll get a confidence interval that goes from about 3.3 to 8.3. Looking back at our data, the ratio of the standard deviations is going to be about 5.2 divided by 4.3, which is about 1.25. So it's probably okay to assume that the two groups do, in fact, have the same variability. So this var.equal true, probably a safe assumption. Here's how these two confidence intervals compare. There's really not much distinction between the two. Assuming that the variances are equal does make the confidence interval a little bit wider. Notice that the lower bound is a little bit lower, the upper bound is a little bit lower. However, both of these intervals suggest that there's a difference between the groups of something in the range of 3 to 8 pounds. So there's really not much difference between these two confidence intervals. We can do a t-test using this procedure as well. We'll set up our null hypothesis about the difference in population means by assuming it's equal to some value. Again, usually this just gets set to 0. The difference in the population means is then assumed to be less than, greater than, or different from some value. We'll calculate our test statistic. We'll let R handle this. We'll calculate our p-value. We'll let R handle this. We'll make a conclusion. So here is how we would test for those differences. In the t.test function, we now have two variables. We have a change variable and a group variable. This notation reads, change depends on group. So this tells me how change and group are related. We are assuming that the difference between the two is 0. The alternative is greater. And again, the two standard deviations were really similar. We get a p-value of 0.000003, so very small. We'll reject our hypothesis and conclude that there's strong evidence that the treatment and control group have different population means. So in the next series of videos next week, you'll learn a little bit about how to extend these sort of ideas to more than two groups using analysis of variance. Talk to you soon.